Welcome everyone for High Performance Computing, our part 2 on our lecture, Practical Lecture 1.1. This is about an introduction to C programming and scheduling. And in the first part, we had really an introduction to C programming with a very essential basics. So not at all a complete C course, and we left out lots of elements of C, mostly because we use C basically here in the course to understand parallel computing, to really understand more the HPC ecosystem software like scheduling, like monitoring, and how the supercomputers leverage basically this parallelism. Hence, this is not a software engineering course where you learn to be a perfect C programmer. We also learned in the first part the motivation why C is still relevant today, especially in high performance computing, scientific computing. And that is true because many of the applications are actually written in C, because basically it's a very fast program. Some are actually also these days in C++. And in fact, we have seen in the Earth system sciences, we still find many Fortran codes, right? So numerical weather prediction and so on has many codes, for instance, still written in Fortran. And the idea was then in the course really in the first part here in this lecture to have a minimum of C program. So we learned a little bit about the idea that in HPC you have certain standards, and when you want to compile a C program, it matters a little bit which implementation you use, because later on in the course we also want to use the MPI standard, right? The message passing interface. Hence we tuned the C programming part already for this, because in lecture 2 and ongoing lectures in the next couple of weeks, we'll be focusing on the MPI. And then we will basically extend this little C program of ours, what we created in the first part of the lecture, in order to then, make it to a full valid MPI program. But this lecture is really just starting from scratch, from the basics. So you don't need any knowledge beforehand. Hence, we had a very small Hello World program. We learned it's basically a text file. And I will revisit, of course, these elements here as part of the second part, where we then go one step further. We have said, okay, when we compile the C program, we had Hello World coming to an executable called hello, which was in a binary. We learned that it's very bad or bad practice, basically, to execute this on a login node. And this is a common operandi, a common modus operandi that is shared in all the HPC systems. Usually, you should use a login node for login, as the name suggests, but of course also for doing a couple of helper tasks. So it's still okay to create directories, to move files around, to manage and organize your file system parts, and all of that. And in some respect, you also can compile if it don't takes a lot of time. So in a way, sees a login as a helper tool, let's say very, very small CPU that should be used not for computation intensive tasks, but rather than for, login. And then what we learned now, to use a login node to submit jobs to the scheduler. Hence, we will revisit the important aspect of a login node and compute nodes. And if you remember a little bit what we had the last time, we said basically in the first part, well, between the login node and the compute node in one respect is a so-called scheduler that helps us to really distribute the software for all the different compute nodes, to not execute on the login node, but to basically submit the job to the scheduler, and the scheduler then take care that this is really run on compute nodes. And this is something that this second part is all about. And so we got to start a little bit by this practical exercises again. We will use basically in the course 2 different software and different, HPC systems. Hence, there are also different MPI applications and implementations. Here we see the one, just that you remember again from Juvels. This has a Parastation MPI, an interesting example of another MPI implementation. And we will revisit this also in lecture 2 and 3 and so on when we talk more about MPI. Also important for us to understand is the size of the system, and this now motivates a little bit the scheduling part, right? When we say we have the Juvel system, it has a cluster module and it has a scalable booster module. So this is part of this modular supercomputing concept that you already know. We have a very huge system, right? And here you see a very interesting snapshot from a monitoring system called LLView here in the red, where all the jobs of all the users are basically shown in the Jureka cluster, another HPC machine, which is also modular, is a cluster and booster model that you see here, but then also the Jewel system. So one important message to take away is really the multi-user aspect of it, right? And this means concurrent access to the HPC system all the time. So basically, this is a system not for yourself, like your workstation with GPUs under your desk. This is in a big hole in JC shared with many, many other users. When they all use the supercomputer at the same time, doing physics simulations, as we just discussed, maybe on Fortran on C, or even with AI, right? You see here a UNet as an example of a deep learning method, which is quite popular these days, where you can use then the supercomputer really to performing a speed up. That's what we also discussed. You want to use HPC for something. And here we basically, with 16 GPUs, really make the training time of such a network smaller and smaller. With one GPU, with 4, 8, 16, you see we basically here create quite some speed up of the training. And that's not where we're stopping, as you learned also in one of my last lectures. In AI applications, HPC is also very popular these days to perform hyperparameter optimization. So this is another interesting part, which partly also is related to something we call neural architecture search. Because in the end, as I said also earlier, the accuracy or error rates successfully are actually somehow hidden in this kind of hyperparameters. But coming back to the HPC system, that means we need some form of a management, right? When all the different users at the same time use it for AI applications, for numerical weather prediction, for other earth science applications, maybe even for chemistry or for neuroscience applications, all at the same time, there needs to be some system in place that basically tells you your job, your activity, let it be this unit we want to train, needs to be scheduled at that particular point in time on these particular part of the system. That's why basically you see here a little bit these colored elements that we will review now when we maybe zoom in a little bit into the Jewel system here as an example. Because the color aspects now essentially say the jobs that you have. You see these boxes here that resemble essentially the real boxes that we have here, right? The racks, as you already know from one of my lectures, with all the node cards, etc., etc. So here are the CPUs and GPUs inside. And this is basically also represented here a little bit in the color. And of course, this is just a schematic view at that particular point in time, right? And this changes over time significantly. There comes a new job, one job is finished. And this is exactly what we call the schedule, basically. And the schedule can have also certain predictions because people submit jobs and basically have long time running jobs, not like our Hello World, maybe for 1 second. Here you see a little bit on the lower part, the schedule. That means in a moment, the system is almost 99.9% utilized, and that's what we want. These are very costly systems, hence it's important that they're actually used quite intensively. But you see also that some other jobs, and you see here the blue line, that's what we are having right now. You see 0 and then plus 2 hours, 4 hours, etc. and how the schedule was before. There are some users that already submitted a very long job, which is still running, and others that may be just about to start. Hence, this is the schedule we talk about. So every time you say to the computer, please submit my job, and I will explain what submit means in later parts of this particular part here in 2. But this is exactly then where we see how the system is utilized over time. And this means waiting. Hence, we call it sometimes also batch queuing system. Because in one way or another, this is something like, as I said, also from the bakery in Iceland, when you get your ticket, you know the number, and at some point in time you will be called upon, and that's your number. Now it's time for your job to be executed or basically get your bread in the bakery. That's something we know from real life, standing in a queue, sometimes not nice. Hence, people use these predictions also, and this view here that you have in LLView, to plan a little bit when they want to submit jobs to see if they are maybe quickly start to run One example is perhaps the weekend, which is sometimes popular with scientists because there's a little bit less load, for instance, and then you can see with the prediction, is my job going to run very quickly? Maybe I want to do a publication and I'm actually short on time. So this is something where experts really derive a lot of information from, also the size of the job that I can really put in. Obviously, the whole system is limited. It has a certain number of CPUs, a certain number of GPUs, many core and multi-core systems, as you know. But then, of course, that means when there are so many users using the system, then it could be that my job will be, just starting tomorrow. It's not sad that it can be actually start today when the schedule is full. You see also a list of the systems, basically usually which has your username, the name of the job. We come to this also later when I demonstrate something on our cluster area, obviously on a much smaller scale. But here you see then these little jobs. You can look on them and basically get some more information, how many CPUs and GPUs requested, how much memory, and so forth. Hence, this is a monitoring system called LLView, and not every system has this. Basically, there are other systems for monitoring, like for instance, Ganglia, that I will also show you later today. So in one way, this is really the summary of saying these systems need some form of manager which, help with the computational jobs. And of course, they should run in isolation to the others. In other words, also not everybody should see the data that you process. So there needs to be a sort of sandboxing aspect to it for, job security with respect to data protection. So this is all done by these interesting schedulers, and hence they are a very important part of the HPC system software. We learned in the beginning of the course that Unix is, of course, something which is also quite important, the operating system. Without this, no computer can actually run. But for HPC especially, scheduling systems are essential, because mostly you will find that the HPC systems are really a multi-user environment, which is a key, which enable then the concurrent access really on these systems all the time. And also there are different scheduling algorithms that are implemented in these kind of batch queues. We will give a couple of examples later. And the example I want to show you is a Slurm really tool that we use on Elia. But in the past, there have been also load leveler, different schedulers exist. And from the monitoring system perspective, they are, of course, also very important information, as you just have seen with LLView. On the Joule system, for instance, we have seen the queue, so we know what jobs come. We have seen the load of the system, but what we didn't say yet, it can be also helpful to understand that some of the system parts are actually not available right now. So in other words, the monitoring system also helps to understand the system health checks, the heartbeats of the CPUs. I told you that in the big installations of all these HPC systems, often elements fail. It could be that some CPUs get overheated in the node cards or in the rack. So the one rack is maybe down for maintenance and they're not usable in the schedule. And you will see that in the monitoring system and get the information about it. So also a very important tool that is often helpful to understand the situation of the HPC system. And of course, it's also for, let's say, beginners, a very interesting tool to, again, understand the multi-user environment. And of course, also to understand that behind these big numbers, when I say, Elia has so and so many thousand CPUs, we have still some nodes like Compute 1, Compute 2, Compute 3 with the real CPUs in. So the structure of the system, the architecture of the system is also something we will explore a little bit with this Ganglia. There's another system we not talk about today, performance analysis, that comes a little bit later in the course. But these two are really essential, scheduling systems and monitoring systems. You have to get that also in your brain. And it's, of course, a focus in this lecture. Hence, there needs to be something when we talk about scheduling, that we manage a certain job, so something we want to do and we want to inform the system about. It's called essentially basically the job script that you see here in the yellow element of the particular system called Slurm. And this gets a specific instruction set that I just go here by 1 and 1. Mail type all essentially means that in any event, when a job is started, the job is ended, you actually get an email, which is quite convenient, right? To know, if you think about, you have a 48 hours running job, for instance, you don't want to hang around for this computer all the time, but you do want to know when it's ending. Hence, you can provide your email here. For us in the course, particularly is important that the Elia system has a partition utin. And obviously, that's not the utin system we had before. So this is really just a partition in the Elia system. When you browse the 2023 and before courses in YouTube, you have seen we used another system called utin. So this is new. And with this, we also need to do some changes in the job script. And this is one of it, to really use a partition utin for us in the teaching part of the course. But there are also other partitions, as I was exploring to the last time, right? When we now go out and a little bit more practically look here again on our web page that we have for the systems, we had the partitions and the hardware, and that you have the partitions that show you a little bit what the name is, what you can do with them, and basically on the hardware specifications, you have also a couple of them describe what CPU is actually sitting behind those. We said, for instance, a high memory capacity module is sometimes noted if you have high memory requirements. You see here, you have quite heavy memory compared to maybe the other compute nodes that you have here, just with 256 and so on. Hence, when we use utin here, that's an example, right? So you have to understand that this is for the teaching part of the course. If you're basically then later in practice as a PhD student or others using the HPC system, chances are that you use the other partitions of Elia. Also, partitions are used in other HPC systems, not only here in Iceland. And so this is a very useful thing to learn anyway. From the number of nodes, we start here very decent with one node. Even the number of tasks per node, we will boil down to 1, where you basically inform the scheduler now how many computing capacity you need, right? And this is a loaded question sometimes, because your job needs to be scaling up for that. You cannot just expect, let's say, that one application that is nicely run in serial, that you then execute on, let's say, 24 nodes, suddenly works nicely in parallel. So your parallel computing job, let's say, for instance, the MPI we will program in the next couple of lectures, needs to be in line with those numbers, needs to really work with these numbers. And that's why we will make a case that the scheduling scripts will be a bit in sync with the applications later. Because we start with Hello World, as we had in the first part of the course, we will boil this really down to 1 node and 1 number of tasks per node that you will see in a moment. Then you can also see the memory usage per CPU. That's also sometimes very important for jobs. The time, it's a concept called volt clock time, where you then have later the opportunity to think about that. Essentially, we can run the job for a certain period of time before it runs against the wall. So in order to specify how long the job should really be and actually should operate. And this is an important part, that essentially when we do this, we inform the scheduler that we basically have a certain runtime in mind. And that means the scheduler can better plan how we actually schedule the job on our HPC machine. And this will be an important factor then for scheduling and also for MPI programs, something that we also explore later. Multithreading is also a very, let's say, special advanced setup. So here also we think about that we have this multithreading environment, and here with output and error, we can actually point the scheduler to the files where should be some status inside. So we want to say something about the output of the job. So how many really have been, giving you, situation of the job in terms of output. So obviously, when we say we write Hello World, then we also want to have Hello World in our output. But let's assume that we programmed something bad, that something was, let's say, wrongly programmed. Then we actually want to also have job errors in the log. And this means, for instance, crashing of the job or misconfiguration on the job. And that is something where we can also learn from what we did wrong. Hence, it's a little bit different than programming on your own laptop. You don't want to be, basically like a typical user of a computer here, because we have this batch system. We put it in a batch queue. we operate it and basically submit the job, let it run, and over time I will get the output, and over time I will get the error. The last one is quite important, because here we think about that the the Python job is essentially very important to specify here, because that's the job we will really want to run in the end, right? So this is an important factor that we also need, because this is in the end our application system. Okay, so here was a short break, unfortunately. But yeah, so let's come back to these applications. And I think when we see the concept of the submit hello world later, it will be very obvious to you, right? The other elements, what we see here, first come, first served, is, for instance, a scheduling policy. That means that the earlier you submit the job, the earlier, of course, your job is getting started. And then if you think about that, basically backfilling, you have a concept which, if there is a hole in the schedule somewhere where your job could actually fill, although many others are waiting for jobs, but they have bigger jobs, right? And the hole might be very small, so that the number of CPUs are not much. Then you can specify this in your job script, and you get actually scheduled before the others, because you actually backfilled into a scheduling hole. So we will reuse these concepts again and again, and then also Ganglia will help us a little bit to understand this concept. So let us go now a little bit more into practice. Again, when we come now to the login, you see that essentially I'm already logged in here in our Elia system. Just checking again, the concept was login node, if you remember. That is what I had here a little bit on the graphics the last time, and that we want to explore now. How to go basically and use a scheduler system. And if you remember the last time, we had this HPC course directory already created, something for MPI, and then our hello program that is essentially in this particular directory. So we had this hello C program, admittedly not a cutting edge scientific application, just more the 101 on learning, how a C program could be in a minimum scale basically work. And this is a valid C program. And we said, okay, it can actually do something. And when we had the kind of compilation for this with the MPI CC, we remembered also we had before to load the module, right? That was another important part of it, so that we have the right module name loaded. And this will be now something we also have to understand, especially if you move later to this kind of MPI environment. So module concept I still have to take with me. So we also learned that I can now, of course, execute the C program, right? So this is now on the login node, hello world. I see the output here, but we learned also at the end, this is not the way to go. So how we can do it differently, how we can use the scheduler starts usually by something where you need essentially the submit hello script. And this is here an example of a very, let's say, small, easy script, understandable for everyone, where we first have the bash defined, and then the sbatch commands here, or the configuration parameters, will inform the Slurm scheduler about certain requirements from your job. And this is something related to name. So here we say the name should be the hello example. Very important, as I told you, was a partition. So we said we are, of course, submitting that on Elia, but we want to have a particular partition Newton where we are from this course are scheduled. We have the authority to use it. So that is something what we want to do. And as I said, with a hello world, we probably don't use a whole number of nodes we have available there. So we're very happy of having one node and actually just one task per node, essentially getting just one core that is executing hello world, but on a compute node. And that's now the important part of it, right? So we don't want to do this on the login node. We do it on the compute nodes. And we have also a way of understanding that and looking into the job characteristica later. So by defining this, this needs to, of course, be in line with your applications. You see also I use my own email here, and then also the mail type that I prefer, that just at the end of the job, I usually get a message. More importantly, maybe, is here really the idea again that modules can be loaded in the job scripts as well. So you have here the module load MPI/OpenMPI 412, what we had the last time, right? That's how I actually used the module load on the command line. And we had with MPI CC, we actually compiled the hello executable. And now you see a code or an application called MPI run hello. Because in later parts, in lecture 2 and the other practical lectures that follow, we will have an MPI application. Then you really need the MPI run hello. In this particular example here, it's a bit, let's say, just preparing this, but still does the job of actually then also gives the hello world out of the cluster. We will extend the hello world example then step by step in the next couple of lectures, so that you understand you do it the same way as you did with a C program, but always do some little bit of extensions to MPI and so on. And that's almost all the magic. It's a text file, right? So we can also use more, for instance, here and there if you don't want to edit with the VI editor. My suggestion is put it in a name you understand. That's why I said submit -hello.sh for a script, for a shell script, so that you name these things a little bit, because you see suddenly in this directory, we have more elements of this hello. We had the hello C program. Then we compiled the C program and basically had also then the hello executable. Then now we have the submit hello job script. So you see more and more elements come to your own small hello job. We have already 3 files, and you can already imagine what these fellows are. These are outputs when the job is done. But this is not the case now. So how can we start the job is something we use sbatch with, and then with this kind of command. Basically, this is now informing the scheduler, I have a job script here. Please use it. And with this, I'm actually scheduled in the queue. Now, because we have, let's say, a very simple job with hello world, it will not take long. So we are not long in the queue, and we are also basically reserved. I already got the email of my iPhone here that Slurm is ready, right? So, but you also see, to recognize which job you have, you basically have the same identity here all over the place. So that means your job that you submitted is unique and you can use for many different things. In the SQ, for instance, if you would have, let's say, a longer running job now, because essentially this is very fast, you see there's actually nothing running, but you see also -a that many other people are using earlier right now, right? So there are jobs in the queue in different partitions, as you see, as I was alluding to before, and everyone is using the system at the same time on different nodes, all the different compute nodes, as you see, but all of them get a different job ID, obviously. So this is a unique number where you can always go back and understand that's the job I submitted. And if you're quick enough, you not only basically see now the job output here, right? That is the same job ID we got when we submitted the job. You see that here. It's basically the 9.3 in the end. And we see also now we have the 9.3 in the end, and we got an output here. So when we go into this output, or let's say, view the output, I think it's not really surprising for you what will be inside. But the beauty is now this was executed on a compute node, not anymore on the login node, right? It didn't came directly back to us. It was scheduled, put in the schedule in the compute node, and then executed and actually put the output in the particular file again. There's one more thing that we also want to know, and this is when we, for instance, do S control It's a little bit elaborate command, which you can actually lots of different things. I use it now here just to show you lots of information about this particular job ID we are interested about, because that was our job. And when you do this over time, this information will disappear again, because if the job too long, old, then this is basically cleaned up. But you see still here from this job number that it was my user ID submitting it. Also no big rocket science, we have seen that. You see the job was completed, which is also good for us. So basically it was running fine. And you can see from the runtime of the job, it was really almost, no op job, because hello world writing out is just basically so fast that normally, of course, you don't want to use a supercomputer for this. But it is a good way to show that we have used the partition U-turn as we should, as we are desired to do, that we are on the earlier eHPC system. And when I then said which of the nodes we got, you see this a little bit. The node list was compute 3, right? So we got the number of nodes 1 as I specified, and the number of tasks was 1 as I specified, and we basically were scheduled on the compute 3 node. And there are some other elements you see a little bit where, my submit script was, where the output was written and the arrows was written, what working directory we had. That's why we had the important phase that we just could say MPI run hello. Otherwise, I should have done much more, let's say, put this whole, directory inside the job. But because we had the submit executed with the sbatch command in a particular directory, this was taken at the work directory, and that's why our hello executable that we have in that wasn't able to be used. Some more information, Morris at HOE, mail type end. That's why I said I already got the email to have done that. And you see that also here in the list. I did this before a couple of times. Always have the same size here, which means everywhere is hello world inside. In a way, that's really it already. So I also want to show you a little bit, of course, the monitoring part of it. But when it comes to the scheduling part of it, this is now very important. There's one thing I forgot, that is the S-info about a particular information. When you have a sort of partition, and we said U-turn is now a partition, we can see that we have the basically compute 1 and 2 nodes and compute 3 and 4 nodes. And actually, if you now compare it, what we had here before, we were scheduled on compute 3. That is not so surprised, because we have indicated the partition and the scheduler saw that basically compute 3 is idle. So let's schedule on compute 3 as a first node in the line. More graphically explaining this, we can move now to something called Ganglia. That's my last couple of minutes before we stop here with the practical lecture. And Ganglia is really the system that we use to monitor our eHPC system. Again, on Elia, when we go into this cluster, we see the load of the, let's say, in the last hour. You can see it's more used at some point in time. It will be one part of you later to find out a bit more in detail. But you also see, and that's now interesting for us, the different compute nodes, right? We have AMD compute 1 to AMD compute 4. We have compute 1 to compute 3. And if you remember, we have been scheduled on compute 3 just before, and have basically, used that system. And there was a mini peak here where you see just that something was happening, and that was probably our job. It was a very small job. So when you have, of course, other jobs that are running longer, you see that here in the other compute nodes, right? Then you have really good statistics, because compute 1 and compute 4 are now essentially our dedicated nodes for teaching, right? There are a couple of professors here that use it for teaching. In chemistry, they also use compute 1 to compute 4, but essentially it's not taking part of the larger scheduling when other users are using it, like here, compute 14. They all have a different load, and they're all different users. And the users, these are those we see in this SQ command, right? Or SQ minus all on all partitions. Come back again to all of these compute nodes. And here you have information who is really using it. And this will be also an important part to understand the load of the system And Ganglia really enables you to go into these different elements in these different jobs and have a good overview about all your different compute nodes. Can see which of them are actually very full. Here's one that is seems to be very utilized, and so on. And you can actually go here to much more details that I'm gonna show today. So I think that's not really part of a beginner HPC course. That would be then already becoming an expert in monitoring. But it's good to understand, and sometimes even if you later dive into science more, you can also use these systems a little bit to explain how your application leverage HPC, so you can put some of the graphics maybe even in a paper. Thinking about the whole summary. So obviously what I just told you all the time here in practice is somehow documented in the slides. You see the job script, which was our start, being part of submit hello. This is an important part. We have the isInfo part saying we have a particular number of compute nodes that's just dedicated for us in teaching on the uTorrent partition. We have seen that actually working when we use this S-control show job ID, which I actually documented a little bit here. You see that in this very large part here where we had the compute node 3, for instance, and so forth. Hence, for you, the most important takeaway message now, we did it the right way. Right? Using your own job script, which you basically had here on the Alia login node, we have done and used this node to S-batch submit hello. It's a common practice in using HPC systems. You use a login system to submit the job to the scheduler. The scheduler needs to know what to do. And this is, of course, something where you come in a lot. So you will steer in later parts of the lectures a number of nodes, tasks per node. You will have different job names. For us, stays a little bit that we use a partition uTorrent, but as I said, if you continue in your career here at University of Iceland, chances are when you use HPC that you use the short partition or another partition. So also very useful elements. And now important is to see these points not in isolation to each other. I said the last time, the module environment is also a very important part, right, that we had in practical lecture 0.1. Hence, it is again connected now to the scheduling part, because you want to reload the same environments that your executable was compiled to, for instance, or to those which the application needs. We will come to also in AI in later lectures around this. So when we have a Python script that is basically using TensorFlow, we're going to use, of course, TensorFlow, CUDA, NVIDIA, and so on as modules, as software. So this needs to be connected. And then the monitoring on top of it shows then all of these and shows that your application is really running on the system. So that's really all I wanted to leave you on the table for today. I think the point is that some of these things we will do in practice in our assignment. So at some point in time, it will get very, very quickly in your head, I think, when you now do the practicals. And it will be, let's say, as I said again, not that you have to program your big C program and so on. So rather we use existing programs here in the course. So don't worry. But important is to understand really the scheduling, the S-batch, and so on, because this is really something which is a heart of HPC, this multi-user and concurrent environment. So thank you very much. See you next time.